Hello everyone, my name is Rémi Pautrat and I'm going to present you our online invariant selection for local feature descriptors developed at the Computer Vision and Geometry group at ETH Zurich. Most current descriptors are aiming at achieving a better invariance to any kind of changes, including illumination, seasonal, and viewpoint changes. However, there exists a trade-off between the robustness to these changes and the discriminative power of local descriptors. Take the example of the rotation invariant shift descriptor and its rotation variant counterpart upright shift, which performs better when there are no rotations. In this work, we propose a new method called LISRD that is able to select the right amount of invariance at test time given the context of the two images to be matched. LISRD for Local Invariance Selection at Runtime for Descriptors. We thus propose an online adaptation to challenging changes in images without losing the discriminative power of the local feature descriptors. Our method is lightweight and the selection only brings a small overhead compared to the current descriptor pipelines. It is additionally compatible with most existing key point detectors and descriptors. Here is how it works. First, we extract a set of local descriptors with different kinds of invariances, and for each of them, we aggregate them into regional meta-descriptors. Each of these meta-descriptors encodes the invariance of one part of the image and can help bringing more context and local consistency when matching the local descriptors. Indeed, at matching time, given two key points to be compared, we can extract local descriptors and their meta-descriptors. We compute the similarity of the meta-descriptors and use a softmax to output some weights representing the probability distribution of each kind of invariance. We then take the average of all the local descriptor distances and weight them with the similarity of the meta-descriptors. This way, the meta-descriptor corresponding to the right invariance, the most adapted, here for example, illumination invariance and rotation variance, will produce the highest similarity and thus will have the highest influence in the final distance. Here's a first use case of our method LISRD applied in the case of rotation invariance only using shift and upright shift. When the object is turned, LISRD is able to select the shift features in blue as it is rotation invariant. However, it keeps the more discriminative upright shift features in red when the object is upright. We also use LISRD in the case of rotation and illumination invariance. For this, we trained 4 learn-dense descriptors, one for each of the combination of rotation and illumination invariance or variance. Here's our network architecture. Given an input image, we pass it through a CNN backbone to compute semi-dense features, which are later split into 4 heads, one per type of invariance. Each head is then tiled in a 3x3 grid, and each cell is then summarized into a single meta-descriptor using a net-flat layer. We thus get a 3x3 grid of meta-descriptors for each kind of invariance. The regional aggregation is very important when different invariances are needed across the same image. Take this example, where both images are rotated, thus the rotation invariant descriptor is selected in both cases. However, there is a shadow on the building on the right, which is not present in the image in the left. In that case, LISRD is selecting the illumination invariant descriptor in green for this building. However, for the building in the background, which is overexposed in both images, an illumination variant is more discriminative and is selected in red by LISRD. In order to train our descriptor, we are using multiple datasets with various changes. First, we use pairs of images without illumination changes, such as in the Microsoft COCO datasets and in the R&D dataset with optical flow data. We also use pairs of images with different illuminations, taken from the multi-illumination images in the wide, and from the R&D dataset again, but this time with images transferred to nighttime using style transfer. For all pairs of images, we augment them with some random homographic warp by controlling the amount of rotation, and we make sure that only 50% of the images contain a rotation. We use for the losses different repeat losses depending on the invariants we want to target. Take, for example, the following pair of images with the same orientation but a different illumination. In that case, the key point highlighted in the two images will be considered as a positive match for the two illumination invariant descriptors. However, it would be a negative match for the illumination variant ones. We evaluated our method on the H-patches benchmark. Here we show the precision at multiple pixel error thresholds, and we use SIFT key points for all baseline methods. On the illumination part, where the illumination is changing for a fixed viewpoint, LISRD is using its illumination invariant descriptors, but it selects the rotation variant ones as they are more discriminative. On the viewpoint side, however, LISRD will use the illumination variant descriptors, which are more discriminative and thus outperform the invariant baselines. However, for H-patches, we have only a small set of illuminations and a few rotations. That is why we created our own dataset. We based it on the existing day-night image matching, which consists of pairs of images, and we augmented them with random homographic warps in order to get pairs of day-to-day, day-to-night, and night-to-night matches where 50% of the images contains a rotation and 50% does not contain any rotation. Using this new dataset, we can evaluate again the precision of our method compared to the state-of-the-art descriptors, again at multiple pixel error thresholds, but this time for superpoint key points. This time, LISRD will leverage its illumination variant descriptor when the illumination of the two images is close enough. But as soon as the timestamp differs too much between the two images, LISRD will switch to the illumination invariant descriptor, and thus is able to outperform the other methods, which are always invariant to light. Same for the rotation. We also evaluated LISRD on the visual localization task on the R&D night local features benchmark. We show here that LISRD is also compatible with any key point detector, such as SIFT, Superpoint, and D2Net. In all cases, LISRD is able to outperform the original descriptor. To summarize, we introduced LISRD in order to overcome the natural trade-off between generalization and the discriminative power of local feature descriptors. It can provide a lightweight online adaptation to multiple challenging contexts. Our meta-descriptor formulation can bring both context and local consistency to the local descriptors. Finally, it is compatible with any key point and most current handcrafted as well as learned descriptors. To learn more about LISRD, please check out our paper and the code available online. Thank you for your attention.